Hey everyone, and welcome to this explainer. This lesson is brought to you by Tutorial Haven. Today we've got a very specific mission. We are going to master the absolute foundations of chemistry so that you are perfectly prepared for those upcoming exams. We're going to take some pretty complex ideas, break them down step by step, figure out exactly what the examiners are looking for, and make sure you walk away totally confident. Sound good? Okay, let's dive right in.
To kick things off, let's use a friendly, completely jargon-free analogy. Imagine a massive pile of mixed sweets. When you look around the real world, practically everything you see, drink, and eat is some kind of complex mixture. Honestly, a lot like a giant pile of candy. Now, in chemistry, before we can even begin to understand how different materials interact with each other, we first have to figure out how to classify them into distinct, organized categories.
So, you might be wondering, how do these sweets actually model the concepts of elements, compounds, and mixtures? Well, think about it. Some of these candies are just single, uniform pieces, right? While others might have a jelly center or different colored layers combined into one single unit. And then, of course, they're all sitting there together in one big, jumbled pile. This exact concept translates perfectly to atomic structures.
All right, so the absolutely crucial starting point is knowing exactly how to define our first category, the element. If an exam asks you to define an element, here is your mental checklist. Ready? An element is a completely pure substance. It's composed of only one type of atom. You can find all the known chemical elements listed neatly on the periodic table. And, most importantly, an element literally cannot be converted into simpler substances by any ordinary chemical process. If it's pure gold, it's just gold atoms all the way down.
But what happens when those individual elements actually link up? That brings us to compounds. Take a look at the structures for three incredibly common compounds: water, carbon dioxide, and methane. A compound is formed when two or more different elements chemically bond together. For instance, just think about a water molecule. It's always composed of exactly two atoms of hydrogen bonded to one atom of oxygen. The elements are chemically fused together in fixed ratios to create something entirely new. And that naturally brings us to our third category, the mixture. A mixture contains two or more different substances, and these can be elements or compounds that are just physically combined together. Now listen up, because here is a massive examiner tip for you. The absolute key difference between a mixture and a compound is the complete lack of chemical bonds. In a mixture, the parts aren't chemically bonded, meaning each constituent still retains its own individual properties. Just like that pile of sweets, you can just reach right in and pick out only the green ones.
Okay, moving on to our next section, physical versus chemical changes, focusing on reversibility and new substances. Now that we know what matter is actually made of, we need to understand how it behaves.
Let's contrast these two ideas because it's a classic exam topic. First up, physical changes. These alter the form of a substance, sure, but not its actual chemical identity. Think about melting an ice cube or shattering a window pane. The water is still H2O and the glass is still glass. There are no new bonds. Crucially, physical changes are typically reversible. You can just pop that melted water back in the freezer. On the flip side, chemical changes are transformations that alter the chemical composition itself. New bonds are formed, creating entirely new substances with totally different properties. And under normal conditions, these are irreversible.
So, how do we actually know a chemical change has happened? Examiners love to ask you for the physical clues. Look for energy changes, like a sudden release or absorption of heat or light. Watch for the formation of a solid precipitate when two clear liquids mix together. Keep an eye out for gas bubbling up or sudden unexpected color changes. If you spot these indicators, bingo, new products are being formed.
Next up, identifying pure substances using the melting and boiling point test. This is incredibly important in the real world. We absolutely need to know that the water we drink and the medicines we take are free of contaminants. Scientifically speaking, purity refers strictly to the complete absence of impurities in a substance. But how do we test for that? Well, we rely on temperature. Pure substances have really sharp, incredibly well-defined melting and boiling points. We are talking about a very narrow range here, typically melting or boiling within just 1 to 2 degrees Celsius.
Now, if you face a practical exam paper, you'll need to know the exact step-by-step for determining a melting point in the lab. First, you place a very small sample of your solid into a tiny glass capillary tube. Next, you heat it gradually in a melting point apparatus. You've got to watch closely and note the exact temperature when you see the very first signs of liquid appearing. Finally, note the temperature when the entire sample is melted. If that range is super tight, say it starts melting at 100 degrees and finishes at exactly 101 degrees, you've got yourself a pure substance.
Let's see how this builds into a highly testable concept,
What actually happens when impurities are introduced? Impurities physically disrupt the orderly structure of your pure substance. What's fascinating here, and hey, another huge examiner tip, is that this disruption has a two-way effect. Impurities will lower and broaden the melting point of a substance, but they actually increase the boiling point. It's like the extra impurities share the heat, meaning it takes way more energy and a higher temperature to make it boil. Oh, and if you run a purity test on a paper chromatography, a pure substance gives you one single crisp spot.
All right, on to our final core topic, separation techniques explained, basically pulling mixtures apart. Since we live in a world absolutely full of mixtures, we need to know how to isolate those pure substances we just talked about.
Because the different parts of a mixture are not chemically bonded, separating them relies entirely on taking advantage of physical differences rather than chemical ones. We can separate things based on their physical state, their unique boiling or melting points, how soluble they are, their density, or even magnetic properties. The specific method you choose depends entirely on the physical properties of the specific items you're trying to pull apart.
Let's look at a really specific one, distillation, which uses heat to evaporate and separate components. But you really need to know the rule for when to use fractional distillation. Fractional distillation is required when the boiling points of the component parts in your liquid mixture differ by less than 25 degrees Celsius. If the difference is larger than 25 degrees, well, you can just use simple distillation. Finally, let's talk about chromatography, which relies on adsorption to separate materials. There are two main applications you should definitely recognize for the exam. Preparative chromatography is basically a purification tool. It's used in bulk to actually separate the components of a mixture so you can collect and use them later. Analytical chromatography, on the other hand, is more like a diagnostic test. It uses really small amounts of material simply to detect if something is present at all, or to measure the exact proportions of a mixture.
All right, let's do a rapid-fire recap of your key exam takeaways. We've covered elements, compounds, and mixtures. We've contrasted physical versus chemical changes. We dove into purity and melting and boiling points, and finally, separation techniques. Before we go, I want to leave you with one final provocative test question to check your understanding. If an unknown liquid boils over a broad range of 102 to 105 degrees Celsius, is it pure? And secondly, what type of change is the physical act of boiling? Think carefully about the rules for impurities and reversibility that we covered today. If you can answer that confidently, you are in fantastic shape. Thank you so much for hanging out with me for this explainer brought to you by Tutorial Haven. Keep practicing, stay curious, and good luck with your studies.